Greetings, Panthers. Dr. Augustine, how are you doing today? Today we're going to take a look at an introduction to calorimetry. Calorimetry is the study or the measurement, the tool that's used to measure the flow of heat in a chemical system. And this video is going to cover actually several different sections in TRO from 7.5 to 7.8. TRO breaks each individual topic of calorimetry down into separate little chunks. I'm going to sort of combine them. So we're going to talk about the difference between constant pressure calorimetry and constant volume calorimetry. That's the first thing we're going to mention. And we'll sort of briefly explain the apparatus used to measure these flows of heat in a chemical system. And then I'm going to show you a systematic way to set up calorimetry problems. And I think I actually taught this class for several years before I kind of figured out what the systematic way of doing it is. And most textbooks, they show you the correct way to do it, but they kind of leave out a couple steps in the beginning. So I'm going to try to show you, starting from the first steps in the beginning, how to break down and solve a calorimetry type problem. Then there will be 3 videos which are going to talk about example problems, all of which we're going to use constant pressure calorimetry. It's just a little bit easier, but it's the same idea. We'll do a sort of a classic one, heat exchange between metal and water, enthalpy of solution by dissolving an ionic salt in water, and then also calculating the molar enthalpy of a reaction. So these second 2 are chemical reactions. This first one is just the heat exchange between a hot object and a cold object. Okay, so let's talk about the 2 different types of calorimetry that one might encounter. So there's one called constant pressure calorimetry, and this just means that the pressure does not change over the course of the chemical experiment. And a way that you can make a constant pressure calorimeter is actually pretty easy. Go to your favorite restaurant or dining hall and steal a couple of styrofoam coffee cups. And if you put 2 of them inside, that is actually a very good thermal insulator. And so 2 coffee cups with some sort of a styrofoam or some heat-absorbing lid, a hole poked through with a thermometer in it. This could be a thermocouple or it could actually be a thermometer. And then you could use a stir rod or you could use something like a stir bar inside, a magnetic stir bar. Anyway, some way to move the liquid around, to swish things around. Usually this is done with a water-based reaction. And so the whole experimental apparatus might cost, I don't know, something on the order of $40 or something like that. And that includes, probably less than that actually, that includes the thermometer, the stir bar. The hot plate would set you back a couple $100, and then the coffee cups would cost you pretty much nothing. This works effectively as a constant pressure calorimeter because if we put stuff in here that we're trying to measure heat exchange with, whatever the pressure is outside, so whatever the atmospheric pressure is at the moment, that will be what the pressure is inside. Now this hasn't filled all the way to the top, but most of them are not actually filled all the way to the top. So the pressure inside of here is going to be equal to the pressure on the outside, and over the course of a calorimetry experiment, the pressure isn't really going to change that much. So that would be a constant pressure calorimeter. Constant volume calorimeter goes by other names. Sometimes this is called a bomb calorimeter, which is kind of a cool name. And what this is an insulated container. So this could be a metal jacket with some styrofoam or some insulation inside of it. With water encased on the inside of it. There would be a little more sophisticated stirring mechanism and whatnot. There would also be a thermometer or a thermocouple of some sort. And then inside of this, we place a steel container, which is what's called the bomb. And inside the steel container would be some ignition wires which go to heat up a reaction. So you might have put your Doritos in here and you have some oxygen inside. This thing is sealed. You run current through the ignition wires, lights the Doritos on fire, completely burns them up. The heat gets transferred from the bomb into the water. The temperature of the water gets measured, and that is how you figure out the calorie count on a bag of potato chips or on a bag of Doritos. Constant volume calorimetry is the technique used most commonly for that. Okay, so let's get into the strategy of actually solving calorimetry problems. And I'm going to start with fundamentals. And this is where I taught this class for probably 8 or 9 years before I came up with a systematic way of doing this. And I'm going to start with the first law of thermodynamics. And the reason I'm starting with the first law of thermodynamics is, first of all, it's always true. And second of all, that's a helpful starting point for us, because we realize that whatever heat gets transferred from one object, gets transferred out of one object, it's going to be absorbed by something else. Okay, so if something is giving off heat, something else is going to be taking it in. And so that first law of thermodynamics is just Q total, the total exchange of heat, is equal to 0. Okay, so this is where I start everything, and this is where the books actually, they don't start here, they start a couple steps further. So a question you could ask yourself at this point is, what makes up the total heat that's going to flow into or out of this system? And that is equal to Q system plus Q surroundings. All right, so if we start every one of these problems off with 0 equals Q system plus Q surroundings, we're in a good place. Now, the challenge that we have when we have a problem is identifying what the system and the surroundings are. There are a variety of different things that it could be, but depending on the problem, then we're going to look at 3 different problems. We'll have 3 different ways to set this up. But I want you to recognize this is our starting point, and then we need to try to analyze what's our system and what's our surroundings. Oftentimes, the system will consist of things like the water that's in here, the metal object that's in here, and the surroundings will be things like the coffee cup calorimeter or the bomb calorimeter. The surroundings will be the calorimeter itself. Okay? Now, if we take this just one step further, we would note that minus Q sys is equal to Q surroundings. And this is often where the textbook starts off. So when you look in a textbook, often you'll see Q minus Q sys equals Q surround, or SURR or something. They're leaving out this step. Okay, it's the same equation, but they didn't start in the beginning. So the beginning place to start is whatever heat gets exchanged is going to be exchanged between the surroundings and the system. The net heat of the entire thing, if you have a decent calorimeter, is going to be 0. Okay? That's our starting point. Now, let's take a look at a specific example. Okay, so let's take a look at this problem. Suppose we have 50 grams of water at 20 degrees C in a constant pressure calorimeter. So remember, that's this type of calorimeter right here, the coffee cups that we've stolen. And we place 21 grams of iron at 90.2 degrees C in the calorimeter and measure a final temperature of 23.5 degrees C. What is the specific heat of the iron? Okay, so what we're trying to do here is we've got a chunk of iron that we've placed inside of here. This iron is at 90.2 degrees. And the mass of iron is equal to 21.0 degrees grams, or 21.0 grams. Okay, the amount of water that we have in here, we have 50 grams of water. And that has a starting temperature of 20.0 degrees C. We'll call this T initial H2O. So that's our initial setup. And remember, we're trying to find the specific heat of iron. So CS of iron is what we're trying to find. Now, we've got a little bit more information here. Assume that no heat is gained or lost by the calorimeter, and the specific heat of water is 4.184 joules per gram degree C. This is a value you could look up in a table. Okay, so let's go back to my earlier discussion, and let's start with Q total equals 0 equals Q sys plus Q surround. Now, let's see if we can figure out what the system is and what the surroundings are. So the system for sure consists of iron, and we could say it consists of water. We could say the water is the surroundings also, but 100% sure that the iron is part of it. So we're going to put Q iron in as my system, and then as my surroundings, I'm going to say Q water plus Q calorimeter. Okay, and it really actually doesn't matter whether we said the system is iron plus water or the surroundings are water plus calorimeter. We'll end up with the same result. Okay, so my system then consists of, for sure, the heat flow for iron, but it's also going to be the heat flow to water and the calorimeter. All of this has to equal to 0. This is our starting point. Now, this little hint right here, assume no heat is gained or lost by the calorimeter. Specific heat of water is this. So what that means, what this sentence, assume that no heat is gained or lost by the calorimeter, that means that Qcal is equal to 0. Or in other words, we can cross that term off the equation. So now what I'm going to do is I'm going to simplify this equation and I'm going to solve for 1 on one side of the equation and 1 on the other. Now we know that the iron is going to give up its heat. It's at 90 degrees C. We already know it dropped to 23 degrees C. So because we know it dropped, we know that iron is exothermic. So it is helpful if we move the iron over to the other side. You don't have to do this, but it just makes the math a little bit less. You have 1 or 2 less minus signs you need to worry about canceling. Okay, so here's our equation then. Minus QFE equals Q water. Now listen, if you get to this point, you're in pretty good shape. Okay, this is an important equation for us now. So here's the next key to solving this problem. There's basically 3 flavors of Q that we could have. We have Q equals MC delta T. That's one flavor. We have Q equals C, capital C, delta T. And then we also have the Q sub P is equal to delta H. So we have 3 different ways we can express Q, 3 different flavors of Q, either MC delta T, capital C, remember that's the heat capacity delta T, or delta H. So at this point, once we get to this equation, we have to look at the type of problem we have and say which of these 3 flavors of Q am I going to substitute in for this value right here. So given the information we have pure water, we have a starting temperature and a final temperature, and we have MC delta T. So for sure the water term, we're going to use MC delta T. In the case of iron, we also have a pure material, 21 grams of iron. We have a mass of the pure material. We have a starting temperature and a final temperature, and we also have the mass, and we're trying to find this. So we're going to use MC delta T for both of these equations. So we're going to do something like this. Minus MFE CFE delta T FE is equal to MH2O CH2O delta T H2O. Okay? And I like to solve these for whatever the variable is that you're looking for. So in this case, we are trying to find the specific heat, right? We're trying to find CS. So I'm going to solve for C of iron. So I'm going to divide everything off over the other side, and we're going to get CFE is equal to the mass of water times the specific heat of water times the change in temperature of the water divided by the mass of iron times the change in temperature of iron. And you might notice I've lost this negative sign. So don't lose that negative sign. That will matter. Okay, and this is a kind of a common mistake that students will make, is they lose track of these negative signs. The delta T's will take care of the negative sign in the problem, but don't lose it when you divide that over. All right, so there's my equation. So now I just need to plug into this equation. So CFE is equal to minus the mass of water is 50 grams times 4.184 joules per gram degree C times, let's see, final minus initial, so it's 23.2 minus 20.0 degrees C. All right, and if we do a check, grams cancels grams, degrees C cancels degrees C, and we have joules left on top. Then if we divide through on the bottom, remember there's a negative sign out front, the mass of the iron is 21.0, and the temperature is T final minus T initial, so it's 23.2 minus 90.2 degrees C. That is the values for the bottom part of the equation. And the units we're going to be left with are joules per gram degree C, okay, which is what we'd expect for this. All right, when we do this calculation, this is equal to 0.48 joules per gram degree C. That is my specific heat of iron. Now, you might be wondering where this negative sign went. Well, 23 minus 20, that's a positive number. 23.2 minus 90.2, that's a negative number. So that negative times a negative is going to turn this into a positive number. We can't have a negative specific heat. So we anticipate this being positive. That's taken care of in this negative change in temperature. All right, next video we're going to take a look at a reaction instead of this example of a metal giving up its heat to water.